Okay, in this video we're going to look at function transformations. And there's a summary of all the transformations right here in this table. But in this video we're going to focus on identifying transformations from tables and from functions written in function notation. And so trying to identify transformations from a table can get a little tricky from time to time if you're not careful in terms of comparing the two data values together for functions f and g. And so what you do is you start scanning the table, and I look and I notice that the x columns are identical to one another. And so really the only difference that we have here is that their outputs are slightly different. So for instance, g of -2 is equal to 6, and f of -2 is equal to 4. And so since I'm putting the same x value into both, and I'm getting two different y values, what I can do is I can create a statement and write g of x in terms of f of x. And that g of -2 equaled f of -2, and all I did was increase its value by 2 units. So f of -2 plus 2. So the -2's here are really just my x's. So g of x equals f of x plus 2. Now in terms of function notation, identifying transformations, if I add 2 onto the very end of a function there, that means my transformation was, I moved it up. The graph of the graph of f moved up 2 units will create the graph of g. Now let's look at another table here. So I'm scanning to see if there are any similarities in the table, and I look and the outputs of f and g are the same here, and what's different are the x values. So both f and g have the same values but at two different x's. So for instance, g of -5 equals 4, and at the same time f of -2 equals 4. So g of -5 equals f of -2. Now I want to write that in a statement where I can write g of x in terms of f of x. And so what I'm going to do is I'm going to let that -5 be x to create g of x that matches this line here, and say, all right, well, how do I rewrite f such that if I put -5 in, what would I do to -5 to make -2? Well, -5 plus 3 creates that 2. So there is that x part that I wanted to write for this statement. So g of x is equal to f of x plus 3, where if I put in -5 into both x's, I would create this same table of values. So in terms of our transformations for f, in order to create the graph of g, if I add 3 to x, that is a horizontal translation where adding moves it to the left. So I moved it left 3 units. All right, another example here. So I'm scanning the table for similarities, and I look, and the x columns are identical, and so I'm basically doing some kind of adjustment to the outputs. And I start looking at what I have. I have f is 4, g is 2, f is 6, g is 3, f is 8, g is 4. So basically, it looks like I am taking and I'm doubling g to make it equal f. So we have g, let's just pick one, g of -2, which is 2, and I have f of -2, which equals 4. And I see the pattern of if I take g and times g by 2, I can make that to be 4. But likewise, what I could do is say, hey, if I multiply f by 1/2, I could say that g of -2 is equal to 1/2 times f of negative 2. The reason why I'm doing that is because of this second line. Write g in terms of f of x. So I want to make g and have this in terms of x's here instead of the negative 2's. So g of x is equal to 1/2 times f of x. Now in context of a transformation, if I multiply the outputs of f by 1/2, I'm doing a vertical shrink. And the factor is 1/2. That's what I'm timesing all of the f values by to create g. Let's look at another table here. So we have some similarities in the column. So the g and the f column are the same. The difference is in the x. So I'm looking for a pattern that exists in the x values between the two columns. And I'm looking, I have negative 2 and negative 4, negative 1 and negative 2, 0 and 0, 1, 2, 2, 4. So we're doubling. And I'm just going to pick the first two again. So g of negative 4 equals 4. And f of negative 2 is equal to 4. So I know that these two things equal. G of negative 4 is equal to f of negative 2. Now our goal is to write g in terms of f of x. So that negative 4 is technically x. So I want to come up with a way to write the inside of f, showing this adjustment of me doubling my x values of f to create g. I'm trying to think of this in terms of, I want to be able to put a negative 4 inside of f somehow and still make it become negative 2. Well, the only way to make it become a negative 2 is to take the negative 4 and half it. Because in order to make this statement that we have over here on the bottom left, we want to make it so we're putting negative 4, the same quantity, into both equations and then reproducing our table. So what we have is g of x is equal to f of 1/2 of x. Because if I put negative 4 in for both the x's, we would create this top line up here. Now in terms of our function transformation, so I know that because I'm multiplying x by a constant, that I am doing a horizontal stretch or a shrink. The way to tell if it's a stretch or a shrink is you do the reciprocal of the number that multiplies the x. So the reciprocal of 1/2 is 2, and that is your factor. So my factor is 2. Basically, that's telling me what I am doing in terms of the size of x, and because 2 is bigger than 1, I'm stretching. So I had to stretch out the f graph to make the g graph, and that makes sense if you look at the table because I'm doubling all of my x's. All right, so now we're going to look at identifying transformations when strictly looking at function notation. And we're going to work through here kind of one at a time. And so I start off with the easy part here. So if I have a function and I'm adding 3 onto the end, that is going to mean my transformation is moving the graph of f of x up 3 units. And I see that I have a couple more things going on here, so let me change colors. I am subtracting 2 from a positive 1x. If I subtract from a positive 1x, that means I'm moving my graph to the right 2 units. And the last thing left that I see is I have a negative being multiplied to f. And if I multiply f, which is really wise, if you change all your y's and make them negative, you are doing an x-axis reflection. Let's look at another one here. So I'm looking here, f of negative 1 times x plus 1 minus 2. Trying to identify the transformations. Well, out here on the very end, I have a minus 2, so I know vertically I'm going down 2 units. And then I try to figure the rest out. Well, you got to pay attention to how the problem is written. So here I have a 1 plus positive 1x. That's important to note because the fact that I'm adding the 1 to the positive 1x means that I'm moving in the left direction 1 unit. And lastly, we have a negative being multiplied to x which means if I make my x's negative, I am reflecting something over the y-axis. So y-axis reflection. Now let's look here at this problem. So this one's written complicated as well, where I have a negative being applied to everything that's inside of here. And I can't jump right in and identify my transformations with the way it's written. I'm actually going to have to distribute this negative very carefully. The negative would be applied to f, but it would not go inside of f. It would stay on the outside. And I would distribute it to the 7 to make plus 7. So this is the line that I'm going to identify my transformations from. Well, we'll start with the easy part. I have plus 7 on the end, so I move my graph of f of x up 7 units. Change colors, look for something else. We have a positive 1x here, and I am adding 4 to it, which means that I am moving to the left 4 units. Change colors. And now I have some negatives to look at. I have a negative being applied to x. So if I make my x's negative, that would be a y-axis reflection. And I have a negative multiplying to f, which means you're negating your y's. If you make your y's negative, you flip over the x-axis. So I have an x-axis reflection. I look here at this problem and I see that I have minus 4 on the very end outside of f, which means that I'm moving the graph down 4 units. And now we're ready to start accounting for what is the plus 3 doing in the negative that's on the x. Well, I have to be careful when identifying my function transformations, especially along the horizontal, because it has to be identified from adding or subtracting from a positive 1x. Well, I have negative x here. So what I would have to do is I actually would have to rewrite that f part, pulling a negative off of those two terms. So it would be negative 1 times x minus 3. So that way I could identify that horizontal translation. Well, that horizontal translation would be determined by me now subtracting 3 from a positive 1x, which means that the graph would go to the right 3 units. And that negative sign, what it did is it created a reflection over the y-axis. Now here we go for another example. Now this one, I don't have any vertical transformations to account for. Everything's on the inside of parentheses. And we saw in the previous example that if we don't have a positive 1x, we need to do a rewrite. Well, the same thing goes if you have a 1/3 times an x. So I might as well go ahead and rewrite this problem so that way I can identify my horizontal transformation. So I'm going to pull out a 1/3 from inside, which is going to leave me with 1/3 times x minus. Now when I'm pulling out 1/3, I'm really dividing. So I divide 3 by 1/3, that makes 9. And now we're ready to identify our transformations. Well, I'm subtracting 9 from positive 1x now, so that means it went to the right 9 units, f of x did. And now we have to talk about this 1/3. Well, the fact that the 1/3 is multiplying to where the x is, I know I'm doing a horizontal stretch or shrink. To figure out which one you do, you flip that number. So I'm going to take the 1/3, I flip it, that makes 3. So since 3 is bigger than 1, this is a stretch. And 3 is the factor. So I made it 3 times bigger along the horizontal. All right, this problem here, we have 3 transformations we can identify. We have a vertical transformation here with a minus 2. I move the graph down 2 units. I'm multiplying x by a number, which means I have a horizontal stretch or shrink. I do the reciprocal of that number, and so the reciprocal of 4 is 1/4. 1/4 is smaller than 1. Now I ignore the sign when I make these calls, but it's positive, so it wouldn't have mattered. So the reciprocal of 4 is 1/4. 1/4 is smaller than 1, which means I shrunk this graph, I compressed it. And 1/4 is the factor. So basically all the x values are multiplied by 1/4 to create this transformed function. And the last but not least is I'm multiplying f by 1/3. F is really your y, so if I'm timesing my y's by a number, I'm doing a vertical stretch or shrink. And I'm multiplying my y's by 1/3, so I'm shrinking them. I don't do the reciprocal of this value. So vertical shrink, the factor is 1/3. All right, next example here. Have kind of a lot going on here, but I see I have +1 on the very end, so that's a vertical translation going up 1 unit. I could stay on the outside of the function here and say, all right, well, we have a negative sign being applied to f, which is really my y, so we did an x-axis reflection. And now I look at the 5 that's multiplying to f. So multiplying all my y's by 5, so magnifying them, that's a vertical stretch. And the factor is 5. And now we look on the very inside of the parentheses, which is a problem because especially when I'm adding or subtracting from x, I have to make that call from a positive 1x. So I have to pull a 1/4 off or out of those terms. So it'd be 1/4 times x, and then that would be minus 4 divided by 1/4 is 16. And so the 16 here that I'm subtracting from positive 1x is how far to the right I moved the original function. So I moved it right 16 units. And now I can talk about this 1/4. Well, the 1/4 multiplying to the x tells me that I did something along the horizontal. To figure out what you did along the horizontal, you do the reciprocal of that number. The reciprocal of 1/4 is 4. 4 is bigger than 1. That is a stretch. And 4 is the factor. That's what you're multiplying by. And last one here. So I'm trying to make or identify all the transformations that are taking place in this problem. I have -5 on the very end, so I have moved this graph down 5 units. I'm looking at it farther. Let me change colors. It's already written nice for me on the inside because I see the horizontal translation, but x already has a coefficient of +1, so I call it like I see it. I'm adding 4 directly to positive 1x. When I add to x, that means the graph goes to the left. And now, stay on the inside, I have a negative being multiplied to x. That is a y-axis reflection. And we got 2 more things to identify here. I am also multiplying x by a 3, so that's a horizontal stretch or shrink. To figure out which one it is, you do the reciprocal of 3, which is 1/3. 1/3 is smaller than 1, which means it's going to be a shrink, and 1/3 is the factor that you're multiplying the original x by. So I'm really starting to compress that graph. And we have one more. I'm multiplying f by 2. So the fact that I'm multiplying f, which are my y's, by 2, I am doing a vertical stretch. And 2 is the factor. So my vertical stretch factor is 2.